Yeah. Okay, good morning, folks. My name is Aldrin Isaac. It's very bright light, so I can't see you. I do have some of my collaborators here, so if you're here, I probably need you for the Q&A if there's time for Q&A. So yeah, again, my name is Aldrin. I'm with eBay, and thank you all for attending my session. What I'd like to talk about here is what has been historically missing from the network telemetry toolkit. And why it matters more than ever in the age of AI. And I know you've heard a lot about telemetry today, but I hope this is a little different perspective on it. So let me start by saying that traditional telemetry wasn't built for the demands of AI. In fact, I would argue that traditional telemetry has never been adequate, even prior to AI. I've been a network operator for 30 years, and I can tell you traditional telemetry has not been good enough. With AI training, however, and as you've heard from previous sessions, when packet drops happen, the consequences are quite significant. And this is why I feel it's important now more than ever that the network industry players come together and deliver a solution that addresses the visibility challenges that network operators face. I mean, there's other various ways of addressing it. You can do it off box through analytics, but I think there's something much more direct that we need the industry to deliver for us. Throughout the conference, you'll hear quite a lot about physical layer errors, which result in lost packets. Physical layer errors are generally simpler to isolate and rectify. So my focus for this talk is on packets that are dropped for all the other reasons, like buffer exhaustion or a missing or incorrect forwarding entry within a switch ASIC. Today I would like to present you with a solution that's pragmatic and attainable with the hope that you will participate in its success. So this picture here represents the telemetry toolkit available to most network operators today. Some have better toolkits, others not so great. So this is more of a general audience thing. This toolkit is primarily SNMP or GNMI based and involves the polling or streaming of low fidelity counters like IFN octets and IFN discards. These low fidelity counters tell the operator nothing about who was impacted by a lost packet and what was the reason for the loss. Counters like IFN discards merely informs us that a loss occurred at a certain point in the network and to some degree in which direction it occurred on an interface. Moreover, traditional telemetry requires that data is harvested continually from every device in the network. The acquisition, storage, and processing of coarse-grained telemetry for indications of network issues is inefficient and expensive. But it's the only option for most network operators given the deployable solutions available today. However, for high-performance drop-sensitive AI networks, this approach, traditional approach, is unworkable. As you heard from the prior session, with AI training, synchronized traffic bursts are a common thing, and they can overwhelm the shallow buffer switches that are predominant in data center networks, which obviously results in packet drops. And many of you are familiar with it, and that's why you're here. Good telemetry should allow us to see the impact of these bursts with much greater precision, revealing insights into the effects of patterns in AI training. With good telemetry, we should finally go from being helpless observers of symptoms to being able to rapidly isolate the causes of suboptimal performance. So now, the traffic patterns associated to AI training can vary over time and over space based on model type, model architecture, and the placement of collectives across the GPU fleet. As workloads shuffle between training runs because of point-in-time GPU availability in a shared training fleet, stress in the network can show up in different places. High-fidelity telemetry must provide a depth of insight that allows developers and engineers to both fine-tune model architecture and placement and workload placement, and even fine-tune physical infrastructure to get the most out of their GPU fleet. So you may have heard of INT or in-band network telemetry. I have links to all of the original standards. Back in 2015, INT promised us fine-grained visibility, but it's not mainstream today. due to complexity and fragmented implementations. It had a lot of potential, but it got tangled up in niche use cases and inconsistent implementations and features across different vendor ASICs. But what I would say is that what operators desperately need and have needed all along and now need more than ever is a simple and vendor neutral solution that is effective and, very importantly, that is practical. So essentially, what most network operators have needed to know is why packets don't reach their destinations. Packets started from one place and didn't arrive at the other. What most operators don't really need to know is what path the packet took, or what the packet's residence time was at every hop along that path. What operators want to know is where the packet drop occurred, why it occurred, and who was affected by the drop. And they need this in a vendor-neutral format, and in a way where that drop data can be overlaid with their existing view of active flows. So I'd like to give a little example that we're going through right now in my own team. We're working to resolve an issue related to packet drops that's caused by a forwarding entry within an ASIC where the forwarding entry is active but has a null next hop. This entry is actually inconsistent with the software forwarding layer, forwarding tables. And it's only visible when you go into the ASIC shell. It took our network SRE team in a large fabric quite a long time, I was embarrassed to say a few days, to isolate the specific device where this drop was occurring, because everything looked fine on the surface. So this is why I want to present to you today S-Flow drop notification. And some of you may be familiar with it. Some operators are probably already deploying it because I believe a few OEMs already have it. S-Flow drop notification offers a simple and effective solution to the problem that I described. Unlike proprietary solutions, it's an extension of S-Flow, a tool many network operators already use. It captures packet drops with detailed reason codes, including drop information that is not available in SNMP or GNMI counters. It does this by leveraging proprietary mirror-on-drop capabilities available today in the current generation of data center switch ASICs. And then by mapping the vendor proprietary drop reason codes into vendor-independent reason codes. So going back to the example I gave before, the issue we were having in our network, with the wedged forwarding entry, S-Flow drop notification would have revealed this issue and the place it was occurring and why it was occurring instantly. Now you may be wondering how any of this has to do with OCP. There are many large networks with network operating systems that leverage the switch abstraction interface, or SI. And SI happens to be an OCP project. One of those network operating systems is Sonic, which is an open source NOS under the Linux Foundation, and you've probably heard or been to the Sonic sessions as well. There was many yesterday, I believe. So what I'm presenting here is a high-level architecture for S-Flow drop notification in Sonic. I'm not going to get into the finer details of this, so I hope you'll review these slides, and I'll be around later to talk more about it if you're curious. But let me point out a few things here unique to S-Flow drop notifications. I don't have a pointer here, but S-Flow drop notification leverages Linux's native drop monitor infrastructure, as you can see from the CN lines, which means both ASIC drops and Linux kernel drops are handled equivalently. And if you're an operator, you know that things drop not just through the box, but to the box or from the box. This means that S-Flow drop notification could be enabled on your Linux endpoints, which gives you drop visibility not just from your ASIC and your NOS, but also from your Linux-based endpoints. So you can see here that homogeneous and accessible end-to-end drop visibility is a core tenet of S-Flow drop notification. Right? Okay. Um, you can actually, you don't even need to use SFlow. You can use Linux's native drop watch tool as well to see what's going on in the drop monitor channel. Another important behavior that I should inform you of is that SFlow drop notification is processed by the CPU. And I know some people are opposed to that, but here's my justification. That's where the CPU is where the reason codes are normalized, first of all, so it has to be that way. And obviously this means that drop notifications have to be rate limited, as you can see over there. It's not unlike SFlow, which processes sampled packets and not all packets. So there's a distinction between drop notification and SFlow. SFlow is sampled, drop notification is rate limited. And there's good reasons for that. So I'm happy to talk a little bit more about this offline, and we can take, if we have time, we can take some questions. But what I will say is that in a storm, you don't need to catch every raindrop to characterize the nature of the storm. And if you did, you would need a lot of buckets. So in conclusion, my ask of you all is this. I appeal to you to help make SFlow drop notification mainstream and finally get telemetry. And I know people have used this phrase a lot, even the last session, but to help us find the needle in the haystack. I think this truly gives us the needle in the haystack. And for this, I am calling on network operators in the room to accelerate the availability of SFlow drop notification for SCI and Sonic using your influence, which basically means your pocketbooks. And I'm calling on switching ASIC providers to participate in defining and implementing the SCI-TAM APIs and underlying mechanisms for drop notifications for your hardware. And there's been a lot of support from ASIC vendors so far, and we look for your continued support in this area. I see Barak over there. So I'm also calling on providers of visualization tools to incorporate SFlow drop notification into your monitoring applications. Today, as you can see from the screen here, Inmon offers a tool that captures and displays both SFlow and SFlow drop monitor data, but more tool providers are needed. And with that, I close my talk. Thank you all for listening, and I hope you will all participate in making SFlow drop notification successful. Thank you again. I suppose if there's any questions, I can take it now.
Questions?
And yeah. Okay.
Thank you, Aldrin, for a wonderful talk. So as an author of TAM spec in SCI, one of the challenges that we were facing is the standardization on the drop reasons. Do you have any thoughts on that, or is there any effort?
Well, what I will say is that, you know, Linux has already standardized a number of different drop reasons. And ideally, we align to the drop reasons that coincide, right? Different ASICs will drop for different reasons that are very proprietary. So what we do allow for is to be able to pass not only a normalized reason code if there is an opportunity to normalize and it's common issue, but also to pass through the vendor proprietary one for troubleshooting. Or, you know, if your upstream application has awareness of that ASIC, you know, it can decode it for you. Yeah. So it's not, we don't want it to be locked in. Things will drop for a multitude of reasons, but in a lot of cases, they drop for the same reasons, right? And in some cases, they drop for very, you know,
yes, I agree. Pick the
reasons,
common denominators.
Yeah.
Yeah, thanks.
Any other questions?
I don't see any other questions. So I have a question on this. You talk about the rate limiting.
Yeah.
Is there a risk of losing?
You will lose.
Unique event?
The point is not to catch every unique event. The point is to characterize what's happening in your network. So even if you rate limit it, say, to 100 packets per second, there's a very, very high chance you're going to be able to get the information you need to take an action. And the point is to be able to take an action, to take the right action, to get the most accurate information, to take the most likely right action. Right? Yeah.
Thank you.
Yeah.
Just to quickly add, I think it's hard to argue against a more generic understanding of why packet drops occur where they occur, right? That makes sense. So I'll agree with that. But one counterpoint that I'll make, which I think you kind of, while answering the other person's question that you touched on, is that there are packets do drop for common reasons. If they do drop for common reasons, and there are like 2 to 3 ASIC vendors or X ASIC vendors there, couldn't you just work with them to actually add observability for those common reasons and get most of those causes for packet drops?
You mean in a proprietary way, or?
No, even in the first approach that you talked about, just in terms of like telemetry, coarse grain telemetry and stuff like that.
Question, I guess, will be, every packet, packet by packet, you can have a different reason for why packet A was lost versus packet B. How do you think you would be able to describe that using standard, telemetry counters, for example? I think that's the hard part. There's no real good place for you to say, well, this packet started from here, it ended over, it was intended to go over there, right? And it dropped at this particular place for a particular reason, for example, like the wedged route, or the network was converging, and it wasn't obvious that the network converging. Maybe the network is converging more than it should, and you're seeing drops, and you say, hey, our network is converging more than it should. Right?
Yeah, that makes sense.
Like, yeah.
I think just thinking about this,
Converging,
right?
rather.
Probably one of the reasons why we should pursue this, at least based on our experience, is when we potentially go to something like lossy fabrics or so, where drops are more common.
Yeah.
Again, a good solution is always, a generic solution always needs to be approached and implemented, but its relative importance increases as drops become more common, which could be lossy fabrics.
So you're suggesting that lossless fabrics never lose packets?
They lose rarely enough that the level of effort needed to build a holistic solution. It's always about motivating people.
Packets because of in the case of lossless, it has to do with buffers, right? Not routes or this or that. There's like 100 reasons why a packet could get lost, not just because there wasn't enough buffers. And that we want to capture all of those possibilities, right? So even with lossless fabrics, you got rid of one reason, but you didn't truly get rid of it because you could still lose packets for other reasons, right? That the system could inform you of something that happened in the ASIC or whatever, right? Or in the fabric in the backplane, right? So and obviously it's harder to do physical, but you have counters for that, right? But certainly for other logical reasons, right? So yeah, I don't, and with UEC and future network architectures, I'm not 100% sure that lossless fabrics is the only way to go. So if we just sit around waiting for lossless fabrics to solve the problem and architecture shift, then we'll be waiting even longer. We've been waiting a long time for something like this because INT got in the way and it just got too niche and it got too fragmented. And what I'm saying is let's all get together and go towards one thing, solves it for both back-end and front-end networks. Right.
That makes sense. Thanks for your talk and your comments. Thank you.
I have one more question.
I come from the distributed systems community, and the only thing that we care about is packets get there, and they get there in order. And so this argument between the networking folks and the distributed systems folks has been going on for decades. Yeah. But a more interesting realization is that Larry Peterson came up with a rant on his blog, and Larry's a very famous network expert. It talks about pairing of packets, and so he lightened everyone to the fact that what we're interested in is that the packet had a pair. In other words, a Shannon pairing of the information that's injected and that's acknowledged. So in other words, returning the packet, just a knack can be useful because then it's paired and you don't have to do timeout and retry. Because it's timeout and retry
yeah.
all our problems.
I hear what you're saying. You're talking about admission control at the receiver, right?
No, I don't want you to get the wrong idea. I'm talking about packet pairing. In other words, you send a packet, you get a NAC. So the thing that we are most concerned about isn't all the other reasons that packets get dropped. Certainly not.
In some ways, that is admission, because you're basically preventing the other guy from sending a packet until you're ready to receive.
I would take a different position than what you're trying to express.
Yeah, I recommend take it offline.
Yeah, we probably should take it offline.
But very interesting talk. A lot
All right.
of interest. Thank you.
Thanks, everyone.